All right. Welcome, everybody, to the third lecture in robot learning from fundamentals to foundation models. And today we're going to talk about imitation learning. First, before we start, a couple of notes on the course structure. We received a bit more feedback from last week, and we decided to move from 3 paper presentations per lecture on Mondays to 2, and we will offload some of the paper presentations to some of the Thursday sessions in that following room. I think Alexei will follow up with an email on this soon, because we were waiting to see who will stay registered and who is not continuing the course before we shuffle things around. Regarding the homework assignments, 2 quick notes. First of all, remember the first homework assignment is due in about 3 days, and there is still quite a lot of students who have not submitted anything or have started working on this. So please, again, don't wait until the very last day to start working on your homework assignment. And for those who already have finished and successfully passed this first assignment, we already released the second homework last week, and this will be due on March 12th. Also, quick note, when you do these assignments, and you work on the autograder, sometimes it's easy to see if you use a lot of AI to solve this, because maybe it takes you many hours for the first exercises, and then for the next ones, you breeze through it in 10 minutes or something. So, try your best to solve them yourself if possible. Cool. So let's start. So last lecture, we defined some notation to help us understand how we can map from images to observations, from image observations, to actions, and we also showed how observations are different, for example, from states when we formalize policies, right? And so we defined all this notation and what are partially observable policies versus ones that have are fully observable. So today we're going to look at imitation learning as a kind of first way to train such policies in imitation by mimicking expert trajectories. So we start typically by assuming that we have access to a data set of expert trajectories, that are not like random movements, but they are sequences of states and actions, let's say human driving or a human teleoperating a robotic arm that successfully achieve some goal. And we assume that these demonstrations are optimal or show optimal behavior to achieve a certain goal. And so our goal here will be to learn this policy, pi theta, that imitates this behavior. In other words, we want to find the parameters theta from this neural network that when the robot sees state S, it produces an action that is as close as possible to what the expert would have done. And so in this example, for example, for the driving in the snowing condition, it would be imitating the action that a human driver would have done. The most straightforward way how to implement imitation learning is an algorithm called behavior cloning, or BC. Some of you might already be familiar with it. So again, it's very simple. We start with this data set of optimal state and action trajectories provided by the expert. And now for a deterministic policy, we treat this as a regression problem, where our goal is to to minimize the difference between the action the expert took and the action that our policy predicts for the same state. And then formally, we optimize this with, for example, doing a mean squared error loss across our data set. So during training, we will sample a batch, do a forward pass with the network to get the predicted actions, compute the loss, and then backpropagate it into the network parameters. And then you do this iteratively with your favorite optimizer, with stochastic gradient descent to optimize your policy. Oh, what's going on here? Sorry. To understand, okay, so this is kind of the vanilla version of this algorithm. Now, we have to look like when does it fail, right? Or how does it work? I think we touched upon this already in previous lectures, but essentially many things can go wrong. Sorry. Okay. Essentially, there are a few different differences to, let's say, supervised learning that we touched upon, I think, in some previous lectures, like the IID assumption. So in supervised learning, as we said, we have this IID assumption over the inputs, that they are independent and identically distributed. This means that your inputs X are independent of the labels we predict. So if you're classifying images of cats, your prediction for the image A does not change the content of the image B, right? And now in behavior cloning, things are a little bit different because this IID assumption doesn't really hold. So let's say that we have like this trajectory over here with this 4 states and this actions that connect them. And now we start, this is what we're trying to mimic, and we start with our policy as at the first state. And then let's say that our policy makes like a tiny error because, maybe like it didn't fully converge, or for many different reasons, maybe like there's just a very, very small error in our prediction. And so it leads us to a state that's kind of like close to S2, but it's not exactly identical, right? It could be just like close to it. And this brings us like slightly off track. Because now this is a new state that we didn't necessarily train on, our next prediction most likely will also be different, right? Because it's like, oh, wow, like we haven't seen this state before, so it's very likely that our prediction will be kind of wrong again. And so this will then like kind of like start compounding, drifting away from the original optimal trajectory because we don't have this IID assumption. So the important thing to note here is that in behavior cloning, the states visited by the policy are not necessarily always the same ones as the one visited by the expert. So there is oftentimes a distribution shift between like the training data set that you train your policy on, and then the test set once you deploy your robot. And you can imagine this, this is, I think, very easily understandable. So it could be tiny things like illumination changes, or, if we collected, let's say, like the self-driving car scenario, we collected all our training data during daytime, and then we drive during nighttime. Or it's like different weather conditions that somehow make the observations look different, and then this will affect the performance of our policy, and it will kind of drift away. Exactly. So given everything we just discussed about distributional shift and compounding errors, the natural question is, does behavior cloning actually work in the real world? And the answer is actually, it can work, it does work. Here, this is a video from 2016 from NVIDIA for a self-driving policy that they train a deep neural network to map raw pixels from a single front-facing camera directly to steering commands. And so, so in the beginning, I don't know if they showed this, it didn't work that well. Oh, look, no hands. In the beginning, it didn't work amazing, but then they kind of collected more data and kind of got this behavior cloning algorithm to work. And so this is, I think, one of this first kind of prototypes we saw from end-to-end driving being deployed in like a real world. So the question is like, why did this actually work, right? Like we just said, like, okay, we have these issues with, drift for states not visited, and for cars, this is like, it's very, very difficult to generalize, right? There is one simple case here for cars that I want to like walk you through on some tricks that have been developed to make to address this issue. So imagine that we have this car, right? And when we drive, usually we try to kind of stay in the center of the lane, right? Like we don't go like doing like crazy curves and drifts and so on, right? So most of our training data will be to just drive straight. Something like this, right? Now, with this drifting error, it can be that for whatever reason we do like, some prediction that doesn't go as well. And, instead of going straight, we kind of start drifting slowly towards the side. This is actually not, this is quite dangerous for cars, right? But the problem is compounded by this effect that, this is a state we have never visited before because all our training data consists of just driving straight. So when the policy like sees this, it's like, oh, wow, this is completely new to me. I have no clue what to do here. And also collecting data for a human driver for such a dangerous situation is difficult, right? Like you don't want to like, crush your car into the side to, learn how to, what to do in such a situation. So that's exactly the problem, right? This is a very difficult state to have in your training data and difficult to recover from this. So to solve this, this NVIDIA paper, they came up with a strategy that involved using 3 cameras instead of 1. So a center camera or two side cameras. And so they applied a very simple trick that essentially they created this, they augmented this data set with examples from the side cameras. And for the camera that's looking left, they labeled this always as, steering right. And for the camera that's looking right, they labeled it all the time as steer left, right? So kind of like creating these virtual actions. And this essentially then tricks the model into learning a recovery policy without ever needing a human driver to actually crash the car during data collection. So this is like quite nice trick to add this fake data to kind of like simulate self-recovery behaviors. Now, this trick was actually also applied here in Zurich. I think I forgot to put the paper name and the year, but it's around like the same time, I believe. And they applied it not for autonomous self-driving, but for quadcopter flying through dense forests. And this is actually very cool because it's kind of like a similar situation for that it's difficult to collect data for flying because like we humans like don't naturally fly. And so what they did here is, do they show? So I think they'll show this in a bit. What they did is they collected they collected data by having humans walk through the forest with a camera rig around the forehead, like essentially with 3 GoPros, and then they would like this way get the same labels of like fly straight. If the camera looks like to the right, then fly to the left, and so forth. I want to show the camera setup. Are they showing this now? Yeah, here we go. So they have this kind of like 3 cameras. And here you can see what the three cameras are seeing, and then they add this virtual labels to learn then how to navigate this terrain. So with like go straight, go right, and go left. Okay, so we know that behavior cloning can be bad, right? But how bad, can we quantify it, how bad it can be? And so we can, for this, kind of derive a formal upper bound on its performance. So suppose we have a time horizon t, the number of steps the robot needs to finish this task, and there's some small probability epsilon that our learned policy pi theta will make a mistake at any given time. And so in standard supervised learning, as we said before, you might expect this error to be linear, something like epsilon t. But if you are, but this is not the case in behavior cloning. And the reason for this is that we can define this cost function where the cost is 0 if the action matches the expert, and it's 1 if it doesn't. And we assume now that the training states, on our training states, the probability of a mistake is bounded by epsilon. However, once we make a mistake, we move into a state that we haven't seen before. And the analogy here is kind of like this tightrope walker example, right? So where there is only a very specific sequence of actions if you want to walk through this tightrope. And like if you drift and fall off, like it's very difficult to recover. I mean, it's not like bad that you die or like you can have like safety or whatever, but like you don't have any demonstration data that shows you how to get back on the tightrope, right? And so the probability of making mistakes for unseen states is unbounded. Yeah, so here's the animation again. And so as you can see here in the summary, if you make a mistake at step 1, you incur a cost of for all t remaining steps. And so if you make your first mistake at step 2, then you will incur cost for t minus 1 steps. And if you aggregate all these probabilities, the expected total error doesn't grow linearly, but it actually grows quadratically, which is very bad. So it's like epsilon t squared. And so this doesn't necessarily mean that behavior cloning is bad per se, but we can kind of bound its performance, right? So we've mathematically kind of like seen that behavior cloning is, not linear, but quadratic. When it starts drifting from the distribution of the states the expert showed. So the question is like, how can we fix this? And so if the root of the problem is that the states visited by the expert differ from the states visited by the policy, our first kind of like solution can be to, well, can't we make them kind of the same or similar? Can we somehow close this distribution shift? And so this brings us to Dagger, or dataset aggregation, which is exactly trying to do this. So the core idea is to make the expert and policy distribution converge by doing online rollouts during training. So the idea is pretty simple. We first roll out the policy in the real world, see what states it visits, and then ask a human to label those states, or we ask experts what action, like what optimal action they would have taken in this state. And we don't throw away the old data, we just simply add this new corrective state action pairs to our existing data set, D. And then we update our policy on this new augmented data set and repeat the process iteratively. And it can be shown mathematically that this will converge to the distribution of state that the policy actually sees, breaking this quadratic error growth. earlier and bringing us to a linear bound. So this is great, but one thing to note is that querying human experts can be difficult and costly in this process. Like it can take a lot of time, and there also might be other issues, like maybe the action space might be different from the robot and the human if you're like labeling this like in hindsight on the computer. But in principle, like paradoxically, this means that behavior cloning actually works better if the data contains more mistakes and recoveries. As I said, like while standard Dagger is quite expensive to label, like if you have thousands of trajectories on hindsight, and there might be discretization errors and so on, we can move to a different version, which we call a human-gated Dagger, or it can also be called online intervention, where instead of the robot collecting data and then human labeling later, we can let the robot run under human supervision, like online. So essentially, this means that when the robot starts making a mistake, a human in the loop can take over and provide a partial demonstration for the remainder of the task. And this is kind of like much more natural and effective, as it lets humans take control only when it's necessary, right? Instead of labeling like the whole thing. And it's kind of like equivalent to, if you're trying to learn how to drive a car, with your instructor by your side, then the instructor will like take over or grab like the steering wheel only like when you're about to crash into the curve, right? It's not gonna like drive all the time. However, this introduces like a new challenge, right? How do you know when an intervention is needed? Like this is like a subtle, but still kind of like difficult question, especially if you don't want like a human constantly supervising the robot and monitoring to decide when to jump in, right? Because this is also kind of costly. So can we move beyond human supervisors? So in order for the robot to learn to recognize its own uncertainty. So can we have the robot kind of ask the human before it crashes? Here I want to show one possible example for how to automate such intervention detectors. And this is kind of older work from my PhD. Here, concretely, we looked at ambiguities in natural language instruction. So let's say like a human asks the robot to fetch a yellow thing for the table, but there are multiple yellow objects on the table. In such a scenario, ideally, the robot should have the ability to detect that this instruction is ambiguous and that we need to query the human back for disambiguation. So in order to detect if an instruction is ambiguous, I won't go too much into the details, but we leveraged like essentially a max margin ranking loss that we trained a comprehension model with. So like with pairs of objects and language descriptions. And so concretely during the training, this loss aims to guarantee that every correct pairs of sentences and objects has scores by a that has scores by a margin M1 that is smaller than any other pair with a wrong combination of objects and sentences. And so this means that at test time, if you have more objects within the threshold, you can consider them potential targets. And so then, like beyond a comprehension model, you can also have a generative model or a head that is able to caption and generate referential expressions for these different candidates so that once we detect that there are like this number of potential like yellow objects that could be applied to, we generate referential expressions for each of them and ask the human about
Robot,
it.
fetch the red thing.
And it looks something like this.
Fetching it. What else do you want?
So we ask, fetch the red thing.
Robot, place it behind the colored dish.
Understood. Placing it. What else do you want?
Robot,
Now this is
fetch the yellow
the
stuff.
example with fetch the yellow stuff.
I'm not sure. Do you mean the middle banana?
And there are like 3 different
Robot, yes.
yellow objects,
Understood.
and then we generate this kind of captions, and then we can ask the user, and then it says yes, like it's the banana that we meant, and then you can keep tidying
Robot,
up your kitchen.
place it on top of the bottom object.
All right, so we've covered distribution shifts, but there are a few more reasons that it would be good to know why behavior cloning might fail. And one of the reasons is non-Markovian behaviors. So for the policy training on the left, we kind of said in the last lecture that like the actions have to be conditioned only on the current state. Or in essence, on the current observation in practice, right? But the thing is that humans don't necessarily choose the actions based on the current state always. Like we don't typically behave like this. So if we see things twice, we might not repeat like the same action. And this might be to different reasons. So one of them is that we, for example, rely on context or history before we, make a decision or take an action. It can also be, our emotional state can also affect on us showing different behaviors, intent, or things we have learned from the past, right? So if you're like a human driver and you see a cyclist, you make some inference, not just by, looking at one image or a snapshot, but usually like it's based on the fact that you track, how is like the cyclist moving in the last 5 seconds. And so you kind of predict how it's going to move. And then this affects like how like you're going to like act as a driver, right? And so if as a robot, you only see like one single image of the cyclist, like the actions that you might choose to predict will be different than if you see how the cyclist is moving through the last 5 seconds. And I will talk about this in a second. Maybe also another issue is that sometimes humans have privileged information. This is very clearly demonstrated when you teleoperate robots. Right, so here you can see me teleoperating a robot during my PhD, and as you can see, like I'm directly like seeing what the robot is doing, right? But now, what the policy is actually seeing are these camera observations, right? And so it's very different because with this camera observations, there are like much more occlusions, for example, that might affect like how you behave. Than like the human here who can also like move around and see more, and this will then lead to different decisions than if you teleoperate just looking at the same observations that the policy is seeing, right? So we also use like the last n frames maybe when we are teleoperating this way. So as aforementioned. If the demonstrations are non-Markovian due to history, like this is bad, right? Because when the robot sees the exact same visual state twice, but sees the expert take 2 different actions, it lacks the history context or to understand why. So our first kind of idea how to fix this would be, well, let's just add history to our policy, right? It's like very simple. Instead of just taking 1 frame of the current time step, we can just take the last, 5 or 10 frames and then, train our policy exactly the same way using our favorite sequence-to-sequence model, right? Like you can take a LSTM, RNN, transformer, whatever, process the last n frames and then train the same thing with behavior cloning. And so, although this seems like a great idea, besides making your model, a bit more computationally expensive, adding history to your policy doesn't always make things better. In fact, it can sometimes make things much worse. Because this brings us to causal confusion. This is a kind of a very known problem for doing imitation learning with history. The issue is here that when we give a high-capacity model access to entire history of observations, sensors, and actions, they typically have a tendency to infer spurious correlations. So because it's essentially looking for the easiest way to minimize the loss, it doesn't always identify the right causal path for it. So imagine that for our demonstrations, like every time the robot opens a drawer, the gripper sensor records a spike of exactly 10 newtons as it grasps the handle. The model will look at this and will think like, aha, I don't need to look at the visual state of the drawer or the arm's position because I see that if the gripper force history shows this 10 Newton spike, then I will trigger the pull action. And now if you deploy this on the real robot, maybe your gripper slips slightly or, it's a bit dusty. And let's say the sensor only reads like 2 newtons. Then the model will be confused because it thinks that the sensor value causes the opening action rather than the visual state of the handle being grasped. And so the pull command will like never be triggered. And so this is like a very kind of, this is like one of the challenges when you train policies with history, like you have to do a lot of regularization and look that they actually still pay attention to the right visual states and so on to learn the causality. Okay, let's move on to another reason why simple imitation learning can fail. And this is what we will be talking about for the remainder of the lecture mostly. Because even if we have like perfect data, kind of a big problem is multimodal behavior in the data. So this means that imagine that we want to like close this drawer, as we discussed in the first lecture. First of all, if you have like a redundancy in your robot joints, there are like multiple ways how you could be doing kind of the same pose with the end effector. And on the other side, for the task itself, there are also very infinite number of ways how you can reach the handle and push it in, right? And because there are like infinite numbers of ways how you can think about this, right? You can do like a side grasp. You can like actually grasp the handle or don't grasp it. You can do it like a top down, or you can do like 90 degrees and everything in between that you can think of, right? Or you can just like push it with the elbow. So humans, when you ask them to record this data, will naturally like do all this, show all these different behaviors. Is that clear? Do you understand? Yeah. And so we have this kind of stochasticity and also expert inconsistency, right? So there are like multiple ways to achieve the same goal. And all are valid in principle because they all achieve the same like success. Now, why is this a problem for behavioral cloning? So if you're using our standard loss function that we introduced in the first algorithm with mean squared error, the math essentially forces the model to find the average of all the demonstrations, right? So if you have like these two tracks, like you're snowboarding or something, and your expert shows you one mode where they go left around this tree, and then another one shows you how to go right across this around this tree, and then the average of those will be like driving straight into the tree, and so this will be a kind of a problem. So what can we do about this? So if standard regression to a single point fails because the average is inconsistent with the expert data, we need a policy that can represent multiple valid peaks of action or modes. So kind of one way, or our first idea how we can solve this is, for example, using something like a mixture of Gaussian distributions. So you represent this with a set of means, covariances, and weights. And the nice thing is that you can model multiple Gaussians, or essentially any distribution that you could model with a mixture of Gaussians. One thing to note here is that you typically need to predetermine how many modes you want. Let's say there are 10. But if you want to control like a humanoid, maybe you want 1,000 modes. And then things start to get quite tricky. What if we want to model? What if we want to represent any arbitrary complex distribution without this constraint? So one powerful way to do this is through discretization. So instead of predicting continuous values for an action, we can kind of turn the action space into grids of bins and then treat this as a classification problem. And so discretization is a good way to represent multimodal distributions, such as, for example, for the drone flying case or the car. But it's kind of difficult to apply naively for higher dimensional spaces because the number you need increases exponentially with higher dimensions. So one solution is doing autoregressive per dimension discretization, which is then linear in the number of dimensions. And you can then use kind of a sequence model like a autoregressive transformer to decompose this. And this is essentially how, let's say, the first VLAs were doing this. Let's do the questions later so we can get on time. How this works is that then you autoregressively predict every action dimension. And with the chain rule, then you can see that this ends up, predicting kind of the probability of the action given the state. So this is very nice, but one thing to consider here is that this will kind of force you to use large autoregressive models like LLMs or VLMs to do that as a backbone, and this might be a bit more expensive computationally. Exactly. So you will kind of sequentially go and predict each individual action dimension. So if it's your 7 degrees of freedom manipulator, then you will predict each dimension separately. Another popular way to handle multimodality comes from generative modeling, especially diffusion. You've likely seen these in the context of generative art, where a model turns random noise into high-fidelity images. We will talk more in detail about this later in week 6, but this is kind of a very, 1-minute version of how you can think about this. The process is twofold. You have the forward process where you can take a clean sample, like this image of a cat, and then you iteratively add Gaussian noise until all information is kind of lost and you're left with static noise. And then you have the generative backward process where you train a neural network to denoise that step by step and learn how to recover the clean data from noise. And so essentially, you create a fake training set by creating images with various levels of noise, and then train this denoising network to kind of predict cleaner versions of the image. Maybe one thing to note is that actually, instead of predicting the full image, during denoising, we actually predict the noise itself, and then subtract this from the current sample to iteratively recover the clean signal. And so both autoregressive discretization and diffusion use sort of an iterative process where one is iterative over the action dimensions and the other over the denoising process. Okay, and kind of the last toolkit to handle multimodality are latent variable models, which can represent any distribution in principle as long as the network is big enough. In latent variable models, the output of the network is still a Gaussian, but in addition to the image, it receives an additional input that is sampled from a prior distribution, let's say like a zero mean variant Gaussian. So this is kind of like a seed for the network. And it will kind of result in the network predicting different modes or different behaviors. So obviously, you cannot just like input random numbers to get the target behavior. So we need to train a model to kind of relate this input latent variables with the desired mode, right? And so you can think of this as, we could have these two modes, like going left through the tree and right, and then we kind of like condition our decoder on this latent to kind of tell it like, oh, it's left or it's right, right? Now I want to address a common point of confusion, the difference between the latent intent and the task specification. So task conditioning is kind of this supervised signal where you tell the robot which specific behavior to execute, like opening a drawer, and so it kind of defines the goal, and the latent variable tells kind of the style or mode within that goal that you wanted to represent. So even for a fixed task ID, the robot might still face infinite ways how to achieve it, right? So as we just discussed with the drawer opening example. Okay, so imagine that now, like we actually want to learn multiple tasks with our policy, right? And imagine that the task is to move the sliding door to the left, right? So imagine this is our task ID, and we are like modeling this distribution. So one thing to note here is that in the real world, it's kind of difficult to define task success, right? So in this example, the robot moves the sliding door, I don't know, around halfway, right? So what does this tell us? Like, did it succeed or not? Like, if we do a poll, like probably like some of you will say like, yeah, I think this is good enough. Others will say like, no, it should be like closer all the way, right? And this is like kind of an inherent problem because there is a tendency to think that the behaviors we want for our agents are a set of discrete tasks, like moving the sliding door or opening a door, or sliding with a door. But it's difficult to draw a boundary where a task begins and ends because they're typically made up of smaller subtasks and skills, and the world is like not discrete, but it's continuous, right? And so, in principle, we would want our robots to learn the full spectrum of skills that are available in the environment. And so this motivates kind of having goal reaching as an objective, where in goal reaching, we define a policy that ends up reaching any desirable goal state from any other initial state on the scene. So you can see here kind of the difference between trying to model like a single task to model like, with a task ID, like a one-hot encoding or like a natural language could also be, or having like goal reaching, so conditioning on two states, an initial state and a goal state. The nice thing about goal reaching is that because the tasks are continuous, the states are also continuous. Okay, so let's put everything together. I will kind of show a case study of how we can combine a latent variable model that handles multimodality with kind of trying to learn like task agnostic control. So one way to do so is using kind of undirected, unstructured play data, where users teleoperate a robot without doing any specific task. And so you kind of like give them like, the teleop and they collect, data. But it's like very, very multimodal. So it's reset free. You don't have to like, reset after opening the drawer. But also, it's kind of like very scalable data because essentially an operator engages in behavior that satisfies their own curiosity, which, if you think about it, is not unlike how children start learning, right? Like they're also kind of exploring and playing with the environment. So how can we now use these latent variable models with goal conditioning to learn from this data? So we start by sampling a random window of play data, such as this one. So this will be like one sequence. And then we encode the last frame of the sampled window through a goal encoder, as we will use goal relabeling to learn control. So this means that we sample random windows of frames and then ask the model to predict a series of actions associated or taken during that sequence to learn how to mimic that, how to reach that goal. Okay, now the trick here is that we address this inherent multimodality in this sort of free-form imitation data sets, meaning that there might be many valid observations that connect the same initial and goal state by auto-encoding contextual demonstrations through this kind of latent plan space with a sequence-to-sequence conditional variational auto-encoder. So we have here this posterior and this prior. And so the posterior will take this sampled sequence, recognizing the exact behavior executed, and then the prior or the plan proposal or sampler will take the initial and goal state, outputting a distribution over all possible behaviors that connect the initial to the goal state. And then we minimize the KL divergence between these two encoders, making the prior assign high likelihood to behavior that were actually executed during play. And then at test time, we will discard the posterior and use this plan sampler to predict multimodal plans. And so the trick here is that by feeding these short horizon goal image demonstrations into a simple maximum likelihood imitation objective, we can now learn kind of task agnostic control in a fully self-supervised manner from this multimodal play data. And critically, conditioning the policy or the decoder on the latent plan frees up the capacity of the decoder to learn unimodal behavior, because you all there's this kind of latent variable. Maybe one last note: can we do this also for language goals? Because for now, this was kind of using the goal images, right, from the feed, from the demonstrations. We can also do this the same efficiently for language. The key insight here is that we can kind of interchange visual goals with embeddings of natural language goals, allowing to learn control mostly self-supervisedly from unlabeled visual play data and reduce the burden of language annotations. I think I'm a little bit out of time to go into a greater detail of the math behind this, but kind of on a very high level, in order to train this, the thing is that we would want to maximize the marginal likelihood of our expert data, but there is kind of one issue, because our Z latent variable is continuous, the marginalization becomes intractable, and so we can't just integrate over an infinite number of possible plans. And so in order to solve this issue, what you typically do is you use a standard variational inference trick, where instead of optimizing the likelihood directly, you optimize a surrogate objective, which is the variational lower bound. And so you have these two terms. The reconstruction, one of them tells you how well does the latent plan explain the expert behavior, and then the other one is the regularization that tells you how close is the Z to the prior distribution over your trajectories. And so when you then introduce goal conditioning, if you have this context kind of variable containing SC and SG, this then nicely aligns with these three components we saw on this architecture, with the posterior, prior, and the action decoder. And the nice thing about this problem is that we have factorized this problem into this latent plan that frees up the capacity of the decoder for learning only unimodal behavior. Side note, a lot of my PhD work also was using like learning from play data and using kind of this latent variable models. So if you're interested more in this, you can look at some of these papers. And to conclude today's lecture, we have talked about imitation learning in its most simple form. We have explained how we can make the states visited by the expert and the states visited by the policy become closer with Dagger and online interventions. And then we have addressed some common pitfalls in imitation learning, such as non-Markovian behaviors from the demonstrators. And we talked also about some possible things that you can do to alleviate them, and also multimodal behavior and a few solutions or tools how you can try to alleviate them. With this, thank you for your attention, and yeah, let's go with the papers.